In section 7.5, we're going to talk just a little bit more about multiplying radicals. We've done multiplying radicals in the last section, but now we're going to have problems where we need to distribute radicals across a sum. So you're multiplying, say, a single radical times the sum of two radicals, or maybe even applying the FOIL technique, first, outside, inside, last, to problems that have radicals in them. And then following that, we're going to talk about division of radicals. Now, there's a special rule we're going to introduce in this section. It's the rule that says we're not allowed to leave radicals in the denominator. Whenever we have a simplified form, there can be no radicals in the denominator. And I'll explain a little bit the reason why that has to be the case. All right? So that technique that gets rid of the radicals is called rationalizing the denominator. So that's what we're covering in section 7.5. Let's get started by looking at a couple of examples of multiplying radicals that involve the distribution rule. In example A, we are given that the square root of 7 is multiplied times the sum x plus square root of 2. Now, because we have a multiplication times a sum, we will distribute to each term. Okay? The thing that I want you to remember as you multiply radicals times radicals is always remember, and I may have said this already once before, I'm going to continue to say it over and over again, it's outside times outside meaning that whatever outside the radical is multiplied times what's outside the radical, and it's inside times inside. Okay, so what that looks like here is, notice x is not underneath the radical, the square root of 7, the 7 is underneath the radical. If I multiply those two together, I get x on the outside, right? Because understood in front of the square root of 7 is a 1. 1 times x is x. There's nothing inside a radical on this x term, so I'm going to have just x times the square root of 7. Now whenever I multiply the next one, it's going to be square root of 7 times square root of 2, which is the square root of 14. Sorry, at this point you also want to check that you can if you can simplify any of those radicals that are remaining. In this case, neither the square root of 7 or the square root of 14 have any perfect squares that you can pull out, so that is completely simplified. So there's your final answer. Look at the next problem. Same approach. We're going to distribute this radical to each of these radicals, keeping in mind the rule that outsides times outsides, insides times insides. Okay, so cube root of y times the cube root of y squared is going to be the cube root. Y times y squared is y cubed, minus the cube root of y times the cube root of y is going to be the cube root. They're both under the radical, so it's y times y, which is y squared. Now, can I simplify either of these? Well, clearly, the cube root of y cubed is just y. I cannot pull out any perfect cubes out of the second radical, so that's going to be the cube root of y squared sticking around, and so that is your final answer. Okay, on the last example you see on the screen here, we have a sum times a difference. Basically, a sum times a sum. It's a binomial expression times a binomial expression. So remember, the rule here is to distribute every term in the first to every term in the second. Whenever you have two terms in each, right, two terms here and two terms here, that means FOIL. First, outside, inside, last. So I'm going to multiply the firsts together. And okay, I'll have 6 times 2, which is 12. I'll have square root of 5 times square root of 5, which is the square root of 25. Okay, when I do the outside, I have 6 times a minus 4, so that's minus 24. And the square root of 5 times the square root of 2 is the square root of 10. Okay, do the inside. That's going to be 3 times 2, which is going to give me a plus 6. Square root of 2 times square root of 5 is the square root of 10. And then when you do the lasts together, you'll have 3 times a minus 4, which is minus 12. And square root of 2 times square root of 2, which is the square root of 4. Okay, at this point we simplify. Notice in the first term, square root of 25, we know is 5. And since this is a multiplication operation between here, I can take 12 times 5 and get 60. Okay, I cannot simplify this any further, but I do notice that I have two terms that have a square root of 10. I can't pull a perfect square out of 10, so again, I can't simplify them individually, but I can combine them because they are like terms. Minus 24 plus 6 gives me a minus 18 square roots of 10. On the last term, I can take the square root of 4, which gives me 2. 12 times 2 would be a minus 24. And the last step, I can actually combine the numbers in this problem into one, and I'll be left with 16 minus 24, which is 36, minus 18 square roots of 10. Now let's move on to division. In division, what we basically mean when we're dividing radicals is we're going to rationalize the denominator. So to simplify a fraction with a radical in its denominator, we rationalize the denominator. The reason it's called rationalizing a denominator is it goes back to what rational means. Remember, I've taught you before in this course that rational means fraction. All right, fraction can mean a number of different things, right? Writing something as a fraction, you see a fraction as a number over a number, like p over q, right? But we also know that square root of, say, 2 is not rational, right? Because if you were to plug that into your calculator, say, you get a decimal number that never repeats a pattern. It never stops, it goes on forever, and it never repeats a pattern, which means it cannot be written as a fraction. Since it can't be written as a fraction, it's not rational, it's irrational. So if we have a square root of 2 in the denominator, that's a radical in the denominator, then we want to rationalize it. We want to turn it into something that is a fraction. We want to basically get rid of the radical, right? We want to turn this into something like, instead of square root of 2, can we turn it into a square root of 4 somehow? Okay, and in fact we can. The trick, or the technique I should say, to rationalize a denominator is to multiply both the numerator and the denominator of the fraction by a radical that will make the radicand, that thing underneath the radical, in the denominator a perfect power. We've talked about perfect powers before, but those are the things that we can actually take the root of. So look at this one. We've got 2 over the square root of 7. So I'm going to multiply. Anytime you see a fraction with a radical in the denominator and you want to rationalize that denominator, you start by just writing this, times a fraction. You're going to multiply by the same thing on top and bottom so that you don't change the value of the fraction, and you're going to even use the same radical that's in the denominator. Now you've got to choose, what do I put under here so that when I multiply it times this radical, I get a perfect square in this case, because we're talking square roots. So clearly I can put a square root of 7 here and a square root of 7 here, because 7 times 7 is a perfect square. That's a nice thing about square roots, by the way. It doesn't work with cube roots and higher roots, but with square roots I can actually always just use the exact same radical I see in the denominator, because if you multiply something times itself, it becomes a perfect square. So look what happens. Multiply straight across. You have 2 square roots of 7 over the square root of 49, which is, right, 2 over 7 times the square root of 7. Now all I did here technically, if you look at this carefully, I have 2 square roots of 7 over 7. I prefer to write it in this form, right? Let me fix that. 2 square roots of 7 over 7. Again, I prefer to write it as 2/7 times the square root of 7, and that's going to come back to a problem that we're going to need to be able to do that. So just for now, recognize that 2 times the square root of 7 is the same thing as 2/7 times the square root of 7. Obviously, I will accept both of these answers, and the computer will as well. but this second form that we've got it in is going to help us whenever we get to problems that have more than one type of simplification that we need to do. Say we're adding we're adding radical expressions together and we have to rationalize in the same problem. We're going to want to be able to write it in this second form here. But the whole point of this example is that you can see I multiply by the same radical on top and on bottom, so that the bottom becomes a perfect radical or perfect power. You take that radical, you no longer have radicals in the denominator. We have rationalized the denominator. For practice sake, we're going to do a few more of these. So let's take a look at example B, where we have y divided by 2 square roots of 5. Again, on all these problems, we're going to start by multiplying by a radical over a radical. Okay, and we use the same radical that we see in the problem. So in this case, I see a square root of 5. And again, what I mean by the same radical is I mean the same index. Now, we may not always use the exact same number in there, as you will see in some later examples. But in square roots, we can always do that, right? What do I have to multiply 5 by to get to a perfect square? Right? The perfect squares are 1, 4, 9, 16, 25. Now 25 is the first one I can get to by multiplying 5 by something. And in fact, I can do square root of 5. And if I do square root of 5 on bottom, I do square root of 5 on top. Now I just multiply straight across. I have y square roots of 5 on top, outsides times outsides, insides times insides, divided by 2 square roots of 25 on bottom. Now simplify that. Square root of 25 is 5. 2 times 5 is 10. I have y square roots of 5 on top, or I can write this as y over 10 times the square root of 5. Okay, so there's your final answer. Now notice how things change whenever we have cube roots in the problem. Okay, cube root of 32a to the 5th over the cube root of b. Okay. Let's begin by rationalizing the denominator, and then we'll have to come back and see if we can't simplify the resulting radicals when we're done with them. So start by multiplying by a cube root over a cube root. Now ask yourself, what do I have to multiply b by to get to a perfect cube? Now if I just stick a b in here, that doesn't work, right? Because b times b is b squared. Cube root of b squared is not something I can simplify. So what do I need to put in here so I can get to a cube, right? I got to get to b cubed. So I have to put in a b squared on top and bottom. Did you follow that? So it's not always the same, exactly the same radical, especially whenever you have higher roots. Now, multiply straight across and see what you get. On top we have the cube root of 32 a to the 5th b squared, right? Insides times insides. And on bottom I have the cube root of b cubed. Okay? Now on bottom, that's easy. That's just going to be b. Cube root of b cubed is b. Now on top, what I need to do there, since I have a radical that has a large expression underneath it, I got to check and see if I can't split it up. Remember the technique from the last section where we simplify radicals? In the section before that, in fact. What we do is we look at 32. We say, can I break it up into a perfect cube times a leftover? Now the perfect cube that goes into 32 is 8. And I'll be left with 4 left over. Right? A to the 5th, I'm going to split into a cubed with 2 left over, and b squared is a leftover because I can't get 3b's out of that, or any multiple of 3. All right, now take the cube root of a cubed, I get, or 8a cubed, I get 2a. So that gives me 2a times the cube root of 4a squared b squared all over b. Okay? There's my final answer. Okay? All right, let's look at example D. Example D is similar to the previous problem, except I've got a radical over a full fraction. All you've got to do to work this one is remember that there is a quotient rule for radicals, that I can write this as the cube root of x squared over the cube root of 3y. Now to simplify the denominator, that is to rationalize the denominator, I am multiplying by a cube root over a cube root. Okay. To get from 3 to a perfect cube, I'm going to have to multiply by 9. Right? The smallest perfect cube that 3 goes into is 27. And I also need 2 more y's to get to a perfect cube of y. Do the same on top. And I have the cube root of 9x squared y squared over the cube root of 27y cubed. If I simplify the denominator, I get 3y. So that is the cube root of 9x squared y squared all over 3y. Okay? I hope by now you're starting to get the hang of it a little bit, but let's do one more example just for good measure so you can see this done one more time. The cube root of x to the 7th, y to the 9th, all over 4z can be written as the cube root of x to the 7th, y to the 10th, over the cube root of 4z. I'm going to multiply by a cube root over a cube root. Okay, the smallest cube root that 4 goes into is 8. So I'm going to put a 2 there to get from 4, multiply 4 to get to 8. I need z squared on top and bottom also, so 2z squared. That gives me the cube root x to the 7th, y to the 10th, z squared, divided by the cube root of 8z cubed. Okay, the bottom becomes 2z. The top I'm going to split up into 2 radicals, the cube root times the cube root, and put leftovers in each one if I need to. So x to the 6th and x to the 1st, that's the largest perfect cube that comes out of x to the 7th. How about z or y to the 9th? And one leftover of y, and then z squared is a leftover. So that gives me x cubed, x squared, because the cube root of x to the 6th is x squared. The cube root of y to the 9th is y cubed times the cube root of x, y, z squared all over 2z. Sorry for the crammed writing there, but that's your final answer. Next, we talk about how we rationalize denominators that may contain more than one term. In fact, we're going to look specifically at ones that contain 2 terms. And I should point out, these are all going to be problems that have square roots in this section, as opposed to in the previous section, or part of this section, part of 7.5, the previous subsection, talked about higher roots as well. But for now, we're talking about square roots. The technique that we're going to use requires something called the conjugate. So I'm putting in here a definition for you. We're going to be using the conjugate both in this section and in a couple sections down the road. So it's important that you understand what a conjugate is. The conjugate of any binomial is the binomial having the same 2 terms with the middle sign change. That's all it means. So conjugate for 3 plus the square root of 2 would be 3 minus the square root of 2. All I do is keep the same 2 terms but change the middle sign. Conjugate for 2 square roots of 3 minus square root of 5, 2 square roots of 3 plus square root of 5. Conjugate for square root of x plus square root of y is square root of x minus square root of y, and the conjugate for a plus b is a, or a plus the square root of b is a minus the square root of b. Okay, now something nice happens when you have square roots and you multiply the conjugates together. Let me show you what happens. You got 2 plus the square root of 3. Say I multiply that by 2 minus the square root of 3. We'll simply apply FOIL. We've already done that in this section, so there's nothing too difficult about that. 2 times 2 is 4. We have a minus 2 square roots of 3 from the outside. We'll have a plus 2 square roots of 3 from the inside. And we'll have a minus the square root of 3 times square root of 3 is minus square root of 9. Okay, so I have 4. What happens here? Minus 2 square roots of 3 plus 2 square roots of 3. That's right, they subtract out. Cancel. Minus square root of 9 is minus 3. You end up with 1. Now what's significant about that? There's no radicals. Right? You took two expressions that had radicals, multiplied them together, you end up with something that doesn't have a radical. Aha, there's a technique. We recognize a pattern here that says, okay, what if I had 2 plus the square root of 3? What if I had this expression right here in a denominator? How could I get rid of the square root of 3? Okay, well, I could multiply by its conjugate. 2 minus the square root of 3. That gets rid of the radical. Aha, that's exactly the technique we're going to use. That's exactly what we want to identify as we go through and see some examples like this. Each binomial had radicals, but the solution has none. So note, to rationalize a denominator with a binomial containing radicals, again, I should actually specify its square roots. Use the conjugate to rationalize. That is, multiply both the numerator and denominator by the conjugate of the denominator. All right, so here's an example. I got 18 over 2 square roots of 3 plus 3. Okay? Now, let me take a sidestep here just so you can see the problem with trying our previous technique. If I were to come off to the side here and say, okay, I've got 18 over 2 square roots of 3 plus 3. Why not just multiply by the square root of 3 over 3? That's what we did in the previous example, right? Why not? Okay, well, on top, everything's fine. 18 square roots of 3. I don't really care what happens on top. But on bottom, notice if I take the 2 square roots of 3 plus 3 times the square root of 3, I have to distribute because it's a sum times a single term, right? So I end up with 2 times the square root of 9, which is 18, plus 3 square roots of 3. Notice I didn't get rid of the radical. What happened? It moved from one term to the other, right? Now if I did it again, okay, well, I got rid of it on the first term. Well, I do the same thing to get rid of it on the second term. Okay, in the numerator I get 18 times 3, which is 54. But on the bottom I've got now, again, having to distribute 18 square roots of 3 plus 3 times the square root of 9, which is 3 times 3, which is 9. Now what happened? The radical jumped back to the other term. And doing this over and over means just that the radical is going to jump back and forth and back and forth and back and forth. We never actually get rid of the radical. Do you understand why the previous technique now fails? Right? So this is not going to help us at all. So what we got to do is apply this technique for the conjugate, using the conjugate. What if I multiply now, instead of multiplying by just square root of 3 over square root of 3, 2 square roots of 3 minus 3 on top and bottom? I'm going to have to distribute and FOIL as necessary, taking 18 times 2 square roots of 3 minus 3, I get 36 square roots of 3 minus 18 times 3 is 54 over, and then in the denominator I'll have 4 square roots of 9. Okay, now the outside and the inside terms cancel. This is a difference. This is a multiplying conjugates together. So I know that the outside, which is going to be the minus 6 square roots of 3, the inside plus 6 square roots of 3 is going to cancel. So I can go straight to the last term, which is minus 9. Okay. Now square root of 9 is 3. So I have 3 times 4, which is 12, right? So all together this is 12. 12 minus 9 gives me 3 in the denominator. Is that okay? Did that all in one step. 4 times the square root of 9 is 4 times 3. 4 times 3 is 12. 12 minus 9 is 3. And on top I have 36 square roots of 3 minus 54. Now I can take the 3 out of both terms here. So 3 goes into 36 12 times, and 3 goes into 54 18 times. So I can reduce that fraction. You got to reduce if you can. Now when you've got multiple terms on top, that means you've got to divide the denominator into every term. But it works. That actually can be done in this case. So we end up with 12 square roots of 3 minus 18. Alright, let's do one more just for practice sake. We have 3 plus the square root of 7 divided by square root of 5 minus the square root of 2 gives me the following. If I multiply the conjugate of the bottom, square root of 5 plus square root of 2, on top and bottom, and then FOIL, both on the top and the bottom. On top I'll have 3 times the square root of 5, which is 3 square roots of 5. I have 3 times the square root of 2, which is plus 3 square roots of 2. I have square root of 5 times square root of 7, which is plus the square root of 35. Okay, and then square root of 7 times the square root of 2 is plus the square root of 14. Okay, on bottom, I have the square root of 5 times the square root of 5, which is square root of 25, minus the square root of 4. Right, and the outside and the inside terms cancel. So I have 3 square roots of 5 plus 3 square roots of 2 plus square root of 35. None of these radicals cancel, plus the square root of 14. On bottom I have 5 minus 2, which just makes this all over 3. Okay, now I can't cancel 3 out of all of these, so that is as simplified as it gets. Now let's ask the most general question there is. If I've got a radical expression, whether it's got multiplication, division, addition, subtraction, or just radicals by themselves, how do I know when an expression containing radicals is completely simplified? Where's my stopping point? Okay, and here's 3 guidelines. Right, first thing you got to have is no perfect powers are factors of the radicands. Meaning for any radical in the expression, you can't pull out any more perfect powers. So if it's a square root, any more perfect squares, etc. The next thing you have is that no radicand contains a fraction, that is a fraction by itself, right? Because if that's the case, then you can use the quotient rule and put a radical on top over the radical on bottom, and then you might have some more simplifying to do. And lastly, no denominator contains a radical. Okay, so let's look at 3 fairly general problems just as a quick review over what we've done so far this section. Okay, this type of radical, single radical expression, it's not simplified because I can pull out perfect powers out of this. Right, these are this is a square root, and it's got I'll say a 27 under the radical. I know I can pull a 9 out of that, which is a perfect square, and also I've got a power here that's higher than my index, so I know I'm going to be able to pull out perfect powers from that. So I write this as 2 radicals, square root times the square root. Right, that is 9 times 3, and x to the 5th. I can take out the highest even number, highest multiple of 2, less than or equal to 5 is 4, so I have 1 left over. That gives me 3x squared times the square root of 3x. Okay, and I know it's completely simplified because there are no perfect powers under the radicals, no radicand contains a fraction, and there's no radical in a denominator. Okay, now the second problem here, it fails number 2. Right, we got a radicand with a fraction, so I write it as square root of 2 over square root of 3. Now it fails number 3. So I've got to multiply by a radical over a radical, and it needs to be, in this case, 3. So I end up with the square root of 6 over the square root of 9, which I can simplify 9. Sorry, that's 3. So I have square root of 6 over 3. Now I can't simplify these. You may be tempted to say, well, I'll mark that out, mark that out. Well, this is inside a radical, this is outside. Remember, outsides with outsides, insides with insides. That is relevant not only for multiplication but also for division. Okay, now we've got several terms to this one. Currently we don't have any like terms, so we're going to simplify each term separately. Okay, the first term, 2 square roots of 3, is completely simplified. There's nothing else I can do there, right? The second one, if I have 4 over the square root of 3, I'm going to multiply by radical over radical to get rid of the radical in the denominator. Okay, and on the last one, I can split square root of 75 into 2 radicals. 25 goes into 75, and that's a perfect square with 3 left over. 3 times 25 is 75. Now let's simplify each of these. We'll have 2 square roots of 3. That's square root of 9, right? Which is 3. So I end up with minus 4 over 3 square roots of 3. Notice this is that trick where I pulled the square root of 3 out front. Plus 5 square roots of 3. Now here's the reason why I pulled that square root of 3 out front, is just so that you can see that I've got 3 like terms now. And it just so happens that the coefficient on the second one is that fraction minus 4/3. So I've got to take 2 minus 4/3 plus 5, multiply that, or I guess add those together and see what I end up with. Okay, so 2 minus 4/3 plus 5. So I got to find the common denominator, since these are both over 1. The common denominator is 3, so this becomes 6 over 3. This becomes 15 over 3. So 6 minus 4 is 2, plus 15 is 17. So I end up with 17 over 3 square roots of 3. Alright, and that's the end of 7.5.